Okay, this is the first of three examples looking at the angles of intersection between lines and planes in three-dimensional space. So, first example, which is example 16 in our notes here, is about how we work out the angle of intersection of two different lines. And the first thing I'm going to do is just draw your attention to this image here. And what we've got are two lines in space. And at some point, unless they're parallel, they are going to intersect. So we've got two lines, and what we can say about straight lines that we know is that they're defined by a point and a direction vector. And in each of these lines here, we can see that we've got some nominal point A, and represented by the position vector A as well. So we've got a point A on a line, and we've also got its direction vector B. So we can say that the line is the equation R equals A plus TB. It's just a formality. In the same way that our second line goes through the point C, and it has a direction vector as well to represent its particular gradient or direction in space. Now, in order to find the angle of intersection of these lines, all we really need to do is to take into consideration the direction vectors, because of course these are that's the information about their gradient. And if you have a look over here on the right hand side, that's a little diagram which shows at the point at which the two lines intersect, those two vectors have a common vertex, and they're going in their particular directions, and we can use hopefully a familiar formula to work out the angle between them, and that is cos theta equals A dot B, the scalar product, divided by the product of their magnitudes. Okay, that should be a familiar equation to you. So all we really need to do to find the angle of intersection of two lines is to extract from the information the direction vectors and then work out the angle between them. Okay, here's example 16. Calculate the angle of intersection of these two lines. So we've got information that we can extract from L1 and L2 about a point on the line, but we don't need that. What we do need is information about the direction vector in each case. So we can say that from line 1, we can say the direction vector is 2, negative 4, 1. And from line 2, the direction vector, we'll call that D2, negative 1, negative 1, 1. Okay? So what do we actually need to do in order to work out the angle? We can say here that the cos of the angle between them, theta, is equal to D1 dot D2, the scalar product, divided by the product of their magnitudes. So if we know where we're aiming for, then we can spend a little bit of time working out all those different things. So first of all, we could say that the scalar product, D1 dot D2, is equal to 2, negative 4, 1, dot negative 1, negative 1, 1, which is the product of the x terms, negative 2 plus negative 4 times the negative 1 is 4, plus 1, and negative 2 plus 4 plus 1 gives me 3. So our scalar product is 3. That means that the numerator is going to be 3. And then I have to work out the two magnitudes of the vectors. I'll do that over here on the right hand side. So we can say the magnitude of D1 is the square root of 2 squared plus negative 4 squared plus 1 squared. Squaring all the components of the vector and working that out. It's 4 plus 16 plus 1 is the square root of 21. Just going to leave it like that just now, and I'll put that into my calculation. And then the magnitude of the second direction vector is the square root of negative 1 squared plus negative 1 squared plus 1 squared. That's the three elements of D2. And simplifying that, they all go to 1. So we've got the square root of 3. So I can feed that back into my main angle calculation and say that our denominator is root 21 multiplied by root 3. And if I do that calculation, I can work out that cos of our angle theta is 0. Roughed up 3 decimal places is 0.378, and using my calculator, it works out that the inverse cos of 0.378 is 67.8 degrees to 1 decimal place. So the angle of intersection of the two given lines, L1 and L2, is 67.8 degrees. Okay, so only using the direction vectors we can extract it from whatever form that we're given it in, and as long as we find the angle between the two direction vectors, that's the angle between the lines. Okay, so next two examples are about planes and then lines on planes, so check out them as well, example 17 and 18.